All right. Thank you. So today I'm going to talk to you about containers at hyperspeed. And as was mentioned, I founded Protocol Labs. And what we do at Protocol Labs is think about the internet, this beautiful machine that we built. And we think about how to make it better. And we try to think completely out of the box or out of the wires and so on. And we try to look at the network stack and say what's missing or what's broken, and how can we improve it. And it's kind of like this. I sort of describe it as like you take the network stack, and then you like add some Tesla and some Tesla coils, and you try to like come up with what's the good, what might make the world better. And you try to make everything well layered so that everything can play nice. This is oftentimes you end up going down the rabbit hole of like formats and so on, and it's kind of like a necessary part of the process. But anyway, I want to start with this image because it's kind of become central to what we do. And it's the first categorization of networks that Paul Baran, I think it's Baran, did for RAND Corporation way back when they were first designing the ARPANET. And he categorized networks in centralized, decentralized, and distributed. And you can pretty much see every single program-based network that we make fall into one of these categories. I mean, yeah, they're very general. But they imply very different kinds of systems and very different kinds of failure modes for systems. And many times even like politics go into this. So you can think of like the ASs as decentralized, like large different governing bodies maintaining control or maintaining connectivity between the network. But you can think about IP as completely distributed with some routers in between and so on. What does this have to do with containers? You'll see. So the talk is structured this way. So containers, Hyperspeed, and then Starship. And I was going to talk about car. I told somebody that I would, many people that I would, but I won't talk about it today. That'll just be like an interesting thing that you'll see. So hyperspeed, containers at hyperspeed. Let's make them really, really fast. So containers, we all know them. They represent a program. They have everything that you need to run that program, or sort of. You still need a runtime, and you still need a whole bunch of other stuff. But at the very least, you have like this hermetically sealed box, and you move it around. And these containers have flavors, right? Like there's different runtimes. We're trying to standardize into the Open Container Initiative is trying to standardize one container runtime, which will be awesome. But regardless, you'll have a bunch of different features with the different containers you make. And regardless, you have different layers of abstraction. You'll have containers within containers and so on. At the end of the day, containers are just files, right? It's just a directory with directories inside and files inside that represents a whole file system of a computer that you want to run. So it's just files representing a VM. There's some other stuff, some metadata and so on, but this is basically it. And what you also have with containers is a set of protocols that allows you to run these files and to make programs happen from them and how to wire everything together. And that's all it is, really. And what's really cool is, Docker really believes this. The value of Docker is not technology, it's getting people to agree on something, getting people to agree on the protocols by which we run this code, and getting people to all come together and agree on a standard. And just to give you a sense, like the IETF and the W3C are the important bodies they are because they make standards, because they get everyone to agree, and we can build like nice layered network stacks like we all use. So I think people in general underestimate the importance of agreeing on a protocol and just everyone implementing it. So kudos to Docker for really pushing that. And yeah, like I mentioned, the container initiative and run C, which is really an exciting little thing. Very cool. So, all right. Some containers are small, less than a megabyte. Some containers are big. Most containers that I've seen are around 50 megabytes to 300 megabytes. That's kind of like the whole OS image. Some containers are huge. I've seen some really big containers out there. I don't know why. I think at some point you have to like break things apart. These weren't even data volumes. Like I don't know what was going on. Anyway, the picture kind of looks like this, right? You are in your computer, you have a container, and you push it to your machines, and you run it there. At least that's where we started. Then you had more machines, and you would push those containers to those machines. And this happens across what I like to call the molasses of the network. So going from your client machine in this side of the ISP, going to the backbone happens through the molasses, like the really, really slow lines to the really fast backbone, right? So here in this room, we have really fast lines and together, and then we have then really fast lines in the backbone. But between us and the backbone, not so fast. And certainly, if you go anywhere outside the hyper-developed cities, it really ends up failing really hard. I was kind of surprised to see that HTTP timeouts are basically blocking a lot of websites from working in many developing countries because you can't complete handshakes in time, you don't complete certain round trips, and HTTP servers just give up on you, which is kind of sad. Anyway, so this was not ideal to push these big images, so of course we had people SSH'd into machines and tried to move containers there and so on, right? And you have, then we said, why don't we represent the container with a file, like the Docker file, and then we push that out, which is really small, and then have the machines recreate the Docker file. I'm giving you this overview that you already know to get you into the frame of mind that we're thinking about. So of course, another developer can come by and do the same thing and push containers and so on. This was good and nice, right? Except that then we started to scale. We had more organizations doing this, and we wanted to, everyone wanted to share containers with each other, so we just started putting them in the Docker Hub. And this was like this great service that just ran, and you could just dump all of your gigabytes and gigabytes of stuff into one place, and they just like ran it for you, which was super nice. And then, of course, we're like, wait, all our code has these Docker files. Let's just push it over to Docker, and then they can build the images and send them to us trusted and so on. This is all really, really good. And we're basically done, right? Like, this is as good as the world can get. Well, no, because it gets more complicated as you scale and scale up, and you get into problems of like trust regions, right? Where you have code that is open and open source and everyone can use, so you put all these images out there in the open. But there's a lot of code that companies use that is not, and so you have these closed environments. And so for that, pretty much ahead of the ballgame, Docker is pushing like the Docker registry and all that kind of stuff, and other people are doing similar things. And so you can keep your areas of trust that way. You use your own private registries for your containers and your applications that you don't want to show to the world. You use the public registry for everyone, and so on. This is pretty good. Except that there's a problem. Like, people can attack these services, right? So we just saw China try to take down GitHub. Like, for a while, I don't know how it was here, but certainly in SF, many companies just couldn't work that day. And like, just tons of value being lost because because these entities were able to attack. And it's not clear who China was. I shouldn't accuse governments. Perhaps we shouldn't do that. But point is, somebody did. Somebody attacked GitHub. And it could happen to Docker too. It could happen to a whole bunch of other services. And if you go back to that image that I showed earlier, this thing, so we started centralized, right? Like we had everything kind of going through Docker, which is like the centralized model. But then we are now federating, which is like the sort of decentralized model with private registries, which is really nice. But then we still have like some points of failure, and we still have some problems. And there's other issues. Not all computers are really, are not connected with the backbone. A ton of devices and a ton of computers are in the molasses region, right? And like they need to be able to ship containers to each other. They need to be able to like download these things. And pretty much everyone in developing countries or IoT devices that are outside of the really fast area can't use this stuff at all because they have to they can't use it in the same way, right? Like, they can't use them by just contacting like the standard registries and so on. And so you have to think about all these other plans of like, how are you going to move around these really big images all the way to these like smaller devices out in the middle of nowhere. All right, so yeah, this picture, right? So what we do is try to push things in the distributed sense. Like, what is the difference between these images? It's that in the different systems run different pieces of code, right? So in the centralized case, you have clients and servers. In the decentralized case, you have a mix of the two, and people are sort of running servers, like people are running registries and people are running clients only and so on. In the totally distributed case, everyone's running the same protocol. Think of it like peer-to-peer. Everyone is just running the same piece of code, and you can cut the reason this is resilient and really useful is that you can cut that mesh in half and still be fine. If the content is in the area that you're in, you can find it and get it and download it. And service will probably degrade, but it's a much more resilient system. And great part of the success of the internet itself is thanks to this. Right, hyperspeed. I'm going to try to go this super fast because it's less relevant, but it's important to cover it. So what is IPFS? It was mentioned. It's a protocol to upgrade the web. We sort of saw that there's a set of problems with how the web works. We waste a lot of bandwidth, so if all of you were to download the same video right now, we would peg the bandwidth of this place and downloading the same set of bits, and this would be totally inefficient and bad. We calculated that of the number of views that Gangnam Style has, that was probably about 477 petabytes served, and this is without counting all the links, right? So this is just out of Google's entry point. Things don't work offline, so the web doesn't, right now if we got disconnected from the backbone, most web services that you use would just not work at all. And this includes really vital and important communication systems. I mean, think about what you use to talk to all your loved ones or your friends or your company. You use web applications that are running in the backbone. And if you move somewhere where there's no speed or something, or the bandwidth is bad, or the latency is too high, or you just can't connect for whatever reason, this doesn't work. And it's silly. We actually do know how to make these things better. We do know how to make applications work in the completely distributed offline case. Gets worse when you start adding all these devices, right? It gets worse when we start going into IoT or just wearables and all this kind of stuff. I would love to be able to run Docker containers on an Apple Watch. Why not? Maybe some size limitations there, possibly. Maybe some protocol limitations, mostly, actually. So it's how you get to talk to the thing and how you get the thing to run your code is part of the problem. So the web is sort of getting pushed out of these devices. And then, of course, this can happen. Your government could surprise you by cutting off your access. That's always fun. This is more like book burning can happen in the web. Things can disappear. So this are the set of problems that we care about in terms of the web. And you're like, what does this have to do with containers? We'll get to it. So IPFS is a protocol trying to upgrade the web by making it more distributed, make it work offline, give it some sense of permanence, making it safer to work within the web, make the movement of content smarter, and of course, make it faster. Because if you don't make it faster, nothing matters, right? All right, why is it called a hypermedia transport? The web is just hyperlinks and media, and a hypermedia transport. So what I mean by hyperspeed is you can make things much, much, much faster if you leverage the web. If you make the web slightly smarter about the links, if you make the links that describe the content embed some sort of information about the content, then you can reason about moving the content much better, and you can maybe not have to fetch a bunch of stuff. This is what Git does. And so if you were to think about what IPFS at an intuitive scale, you would see a stack like this, a set of ideas that come together to craft IPFS. We're not actually using, well, we are using a DHT and we are using the web, but we're not actually using Git or BitTorrent. We are just taking ideas from those protocols. And so it is a suite of protocols that are meant to work with a whole bunch of other stuff. So we have this stack, this layering of protocols where we mean to make a transport that is completely network agnostic. You can run it over UDP, you can run it over WebRTC, you should be able to run it over WebSockets, over Tor, whatever. And you should be able to choose different kinds of routing and discovery protocols. All right. This is a Merkle tree. Think of the Git data structure as a big tree with Merkle links. Merkle links just mean that you take the content, you hash it with a cryptographically secure hash function, and you use that to address the content. All right, that's kind of weird. What does it give us? Well, it gives us the ability to verify all the content all the way, right? So if you've used Git, I'm sure that most of you have, you get this amazing capability of trusting that the data and the bits in the middle of the repository are not going to suddenly change on you because the hashes won't check. And so that way you know that things are fine. And the thing about Merkle trees is that they're everywhere. Tons of applications use them. In fact, the last talk was talking about using hash chains, or they're sort of commonly referred to as Merkle trees. I don't like that name because it implies a specific construction. And so hash chains is another name. We've called it Merkle DAG as well, and so on. Bitcoin, by the way, is a Merkle tree too. And people say that money doesn't grow on trees. So what IPFS is intuitively a big Merkle forest. This is the only place that I like using the Merkle tree analogy because it works really nicely for this. You can think of IPFS as a transport for all these data structures. You can layer it in the web that way and move around entire repositories, move around blockchains, move around hash chains like the notary stuff. You can think about these representations of files, and you can think of like a tar archive as constructing. You can construct a graph out of a tar archive the same way and Merkle link everything. And you get much more security out of this, but you also get speed out of it. Because if I have a whole bunch of objects in my machine, and they all hash the same thing, then it's the same stuff, right? So if you're going to send me a huge file, and I already have 50% of it, because I can check those hashes, then you only have to send me half of it, right? And when you think about containers, most of the stuff is duplicated. Even if you got all your layering right, sometimes you still end up producing the same content, and you still end up producing the same files. And so layers, today, I think the Docker layers are changing. I found out today that it's getting a lot better in the future. But you can still end up sending the same files over and over and over again. And certainly the case with, for example, run C, if you don't have like the nice layer model on top, you'll end up sending the same files over and over and over again. So that's what I mean by hyperspeed. If you use Merkle links, you can reason about the content, you can reason about the graph, and move only what you want. This is what made Git successful, by the way. So we were back in the old days, we had CVS and SVN, a totally centralized model. And what sucked about that is that if you got disconnected from the central server, you couldn't do anything. You couldn't commit, you couldn't work at all. If the central server died, well, nobody could. And Git has what I like to call the honey badger strategy, which is that it is a totally distributed protocol, and it just works all the time, no matter what the network looks like. And so you cut off a piece of the network, no matter if you're on that side, it doesn't matter at all. You can still exchange objects with each other. You can still work. You can still commit. Honey badger don't care. If you take out the service completely and you disconnect everyone from the backbone, you can totally still work. Honey badger don't care. You can still commit locally, you can still send objects to each other, and this is the power of Git. And IPFS works the exact same way. So we're talking about representing the entire file system, so the entire Unix file system and the entire web, so all of that, as a massive Merkle tree. So, said that, let that sink in. So that's how we can get hyperspeed everywhere, right? Like we can talk about reasoning carefully about where I'm going to fetch some data from a server, from a web server while I'm browsing, like while I'm finding a video or something. I might not need to download any of it at all, or maybe I need to download pieces of it. And you can tack on peer-to-peer systems to find each other, for example, in this room, and understand what content is available in the network and pull it from each other, like leverage the network itself to help distribute the content in a much smarter way. And you can put caches, you can put content caches in buildings, right? It's not actually that expensive to ship a machine into this building that has a whole bunch of disks and just pre-fill it with stuff that is likely to be requested by people. That's a hard question, what is going to be requested? But turns out that Amazon can do it for what you're going to shop on, so I'm pretty sure we can do it on what people are likely to download. For example, if you know that people are developers and so on and pull images all the time, you can think of it as within your control. When you run your own registry locally or something, you can reason about that and have automatic fetching of things. So Git is just a bunch of files, right? And commits are just like the special file that's pointing back with Merkle links. And so the power that it has is because it only has to store things once. And again, containers are also just a bunch of files, and they work in a similar way. I mentioned that the layers didn't work that way. That's because the layers right now are tars, where you kind of like overlay all of these, and you get a projection of what all of them together mean. But if we move layers to look like this, it'll be much more secure and much faster. So when I first saw the layers thing, I kind of like didn't understand it for a while. Maybe there was a reason that I don't get about why it was structured this way instead of like the standard Git all way. Part of it is probably that Git is not good at really large files. We had to struggle with this, and so that's why we wrote our own thing, because we chunk really big things into smaller pieces, and so on. Right, I have very little time. So Starship, what the hell is this thing? We are announcing a thing called Starship, which is a very simple application layered on top of IPFS, which is 4 containers. It's what we call a hypertransport, because it's moving around objects using Merkle links. We don't have a logo yet, but these are some possibilities. And it's going to work with every flavor of container you have. So the idea is to do something that you don't have to think about compatibility between container systems, and you can move around images and content and deduplicate across things, right? So if you have a Docker container and you have a Rocket container or a Runc container or whatever, you should be able to just deduplicate a lot of content anyway. So that's where we're headed. And it'll work. You'll install the same thing on all machines. So instead of thinking about a I don't know, like some machines run a client, some machines run a registry, and so on. It's the same thing. Everyone runs the same protocol. Everyone just runs a Starship. And some machines will carry more stuff and some less, but the point is that you can use any machine for anything, should you need to. And so the model looks a little bit like this. You have these servers running Starship. Some of them you control, some of them you don't. You have some clients, and you move around containers by just telling Starship to push things or pull things. So we're trying to match every single interface that people are used to in their container world, right? So in Docker, you push and pull images. In other systems, you'll do exactly what you need to there. And so the idea is to not feel anything strange at all, but have it work. I have 1 minute, which is really short, so I probably can't show you the live demo, but I'll just walk through it. So Docker ship is the Docker-specific version of Starship. And it's a very, very simple thing. It just, you just have to initialize it, you start it, and then you push images into it, and you pull images out of it. And that's it. That's all you have to reason about. And so it will, when you push images into it, other Starships that are connected in the network will be able to pull them out. And then there's some complexity when you reason about when you want to move something to specific locations because you know that an image should live somewhere. And we'll get to that, but it's not really important. The very basics of the demo looks like this. So I had it here as well because the Wi-Fi was not amazing, so I also put it on these slides. So you init in your local machine, and what that does is that it creates an IPFS repository inside your machine. And this is the registry version this is demoing. Then you would start, and in this case, Docker ship would start inside a Docker container. And it would start a process within Docker. And that is running IPFS, and it would be running a registry. And then you find some image that you want to push, and then you push it into it. And you go into another machine. You'll, of course, be able to push with the names and so on. That's not fully there yet. You go to some other machine, you init as well, you start it, and you pull an image out. And you're like, wait, how did this happen? Well, these stations are connecting to each other. By default, they connect in a global network, but you can have them connect in a private network. So, if you do Docker ship peers, you see the peers that they're connected to. And you'll also have then you can connect to specific ones, and you can, of course, make your own private network that nobody else can touch because you can encrypt all the transport with a key. And as I mentioned, we're going to have 3 flavors of the Docker ship because there are different use cases. Some people, so we can totally use the registry and make it as a storage driver. So it'll look exactly like a Docker registry. Nobody will have to think about it, and it'll just work the exact same way. But it's just storing things into IPFS. We'll have a Docker graph driver itself, so you can bypass the registry, and so just have it as a plugin there, kind of like how other people are starting to do graph drivers. And you can, the totally uninvasive way is to just do standalone. And so this loads and saves into Docker, which is annoying because it ends up replicating some disk space, but it works. Cool. So that's continuous at hyperspeed. I wanted to show you one thing. I can show you the demo and so on, but I don't think we have time. This is what an image looks like inside of IPFS. So this is an image that was imported into IPFS, and these are all layers, and there's stars in here. This will deduplicate as well. We haven't gotten to parsing all of the specific Docker format yet, but you can see here that across different layers, it just deduplicated all of this. I think it's actually zeros, but there's other pieces that are deduplicated as well. This doesn't show like all of the files, but these are like the different blocks that would be part of your image. Cool, and yeah, so I guess that's it. I don't really have time for more, but if people see this and are kind of interested, come by, and we'll also have like a more extended demo that we'll record and show you, and so on.
Is it open source?
Amazing. Absolutely. So everything we do is totally open source and MIT licensed. So we do MIT license and the new patents file, like the one that Google made for I think it was Go, or one of these services. So it has like the Apache 2 patents thing, but it works with MIT license. Yeah. So yeah, this is Docker ship, and it works on top of IPFS. This is an explanation of how to use IPFS for different kinds of systems like this. If you had to guess, how many lines of code would you think that this Docker ship is?
3.
That is a good guess. Not that few, but it's less than 100.
Oh.
It's just a few shell scripts wrapping IPFS. So IPFS is doing all of the heavy lifting of connecting to other things, finding each other, announcing the images that are there, and pulling them and moving them around. So yeah, we'd love to have you try it out. It's very early and rough. It's not super polished yet. But if you're fine with that, come talk to us, and we will show it to you, and you can use it and all that kind of stuff.
Thank you very much. That's incredible.
Thank you.